tangent vectors, right?
Yes.
Then why don't we define the tangent space on a manifold by by pushing forward the tangent vectors at a point inside Rn by the inverse map or inverse.
Map
I
of the
mean, we have
chart.
a chart. There is those are Yukomo phi, right? We can push forward by phi inverse.
Yeah, absolutely, absolutely. But that would depend on the chart, right? That's the whole point. Yes, you're absolutely right. Of course. I mean, a manifold is locally Euclidean, right? So locally it looks like a piece of Rn. So in Rn we know how to talk of tangent vectors and tangent spaces there. So you can just push forward by that chart and define it. But that would depend on your chart. So we the definition we were trying to get to, and we did last time, was something which is intrinsic to the manifold. It doesn't depend on a choice of an atlas or a choice of a chart, etc. Okay, so but eventually when you work with smooth maps and their derivatives, you would have to work with some choice of atlas. I mean, usually when doing computations, you would choose some atlas and some chart around some point and work with that. But that this is just to and we'll justify that. Today, in the first part of today's talk, we'll be talking a little bit more about these derivatives of smooth maps between manifolds, and maybe see an example of how we use charts to kind of do sort of computations, do parts of some argument perhaps, but it's not sort of as a notion. It has to be independent of what a chart is. So that's the notion that we have defined. All right. So
Sir, these two vector space will be isomorphic as well, right?
what the ones that I've mentioned here?
I mean, the ones you have defined already, and the one taking the inverse of the chart map and looking at its push forward.
Yeah, there will be definitely. Yeah, exactly. Yeah, absolutely. That will be isomorphic. We haven't yet gotten to that. Yes. So that was one of the first things we'll do uh, today, right? Yeah. So right now, so let me sort of go back to sort of this recap. So last time this is what we saw, right? We saw I sort of motivated that abstract definition of tangent spaces, of tangent vectors and points in the manifold by looking at what tangent vectors are in Rn, and so one of the things we observed was it's this. You can think of tangent vectors in Rn as operators, as directional derivatives. So that defines an operator on the space of smooth functions in Rn to R, right? So and of course this is all sort of tangent vectors in Rn, let's say based at a point x, right? And these and so this is what this tangent space can be then thought of as. So TP of x, the tangent space, well, TP Tx rather, sorry, Tx of Rn, this tangent space can be thought of as the set of all such directional derivatives that uh, this is what we call derivations. So let me just write that. So the derivations of these linear operators satisfying certain properties, right? So derivations at x, right? And so this definition we 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 can now transplant to a manifold. Okay, so somehow, if you have a manifold, let's say you have a sort of a torus or a sphere or something, and you have a point x on it, right? So that's your manifold M, and so you're not so the way that we've defined it, the manifold is just locally Rn, right? So we haven't sort of we are not putting it inside some bigger space, a bigger Euclidean space yet. Okay, so the way that I've drawn it is the torus that you think of as sitting inside R3. It's a two-dimensional manifold sitting inside R3, but we haven't quite done that, right? The way that the torus is defined is defined by gluing together, two-dimensional sort of open sets, right? Open sets in R2, right? So you need some definition of a tangent space that doesn't rely on such an embedding, so it doesn't rely on M sitting inside some bigger thing, and also it shouldn't depend on an atlas, and so this definition, so using notion of derivations sort of applies even in this manifold setting, and we can just say that the tangent space to M is the space of derivations at the point X. Okay, and then here, so derivations are now these are linear operators, right, from smooth functions on the manifold to R, so sort of linear operators satisfying the Leibniz rule. Okay, so we kind of concluded at the end of the class last time that that's the sort of the Leibniz rule is enough. Somehow there was a third axiom which we had started off with at the beginning, saying that this linear operator shouldn't depend on sort of what happens far away from that point, right? So X. It should only depend on what the so the smooth functions, when it's operating on a smooth function, giving you a real number, it should only depend on what the smooth function is in a neighborhood of X. In other words, it depends only on the germ of X, of F at X. Okay, so the technical term here is germ. All right, and so. So that axiom that we had introduced in the beginning, we saw was actually a consequence of this, the Leibniz rule and the linearity. Okay, so anyway, so this space of such linear operators satisfying the Leibniz rule, the space of these derivations at X, these form a vector space, and that's what we defined as tangent space at the manifold to be, right? Yes, so now the one of the things we'll do is to relate that to more familiar notions again. So like Bappa was mentioning, so if you take a chart now around that point X, let's call it U, this maps to some open set in Rn, right? So this phi of U is some open set in Rn, and that's a homeomorphism, and so you can talk of phi inverse, which is the parametrization going that way as well, and you can use this phi inverse, etc., to talk of the tangent space. So X will go somewhere. Maybe X goes to the origin here. So you can think of, you can talk of tangent vectors based, let me use some other colors. You can talk of tangent vectors based at 0, in Rn, just like you sort of normally think of, and then you can sort of imagine that so via this chart you sort of push forward these vectors, and you get some kind of define some something here which you can think of the tangent space as well. So we'll make this precise, so you can think of this abstract definition, so that by the end of what our discussion in the first part of the class today, so you can think of this abstractly defined sort of vector space in terms of the usual notion of tangent vectors or vectors in Rn. Okay, so that's the sort of the goal. So the goal would be to also kind of connect it with as somewhat more familiar notions. Okay, so so that's the plan right now. So so sort of maybe let me write it down. Sort of so the first goal today is to sort of see that that this tangent space is actually sort of isomorphic to Rn. Okay, so just like sort of tangent, and you can sort of and can be sort of can use the charts to sort of deal with it. Okay, so you don't really have to deal with this abstract notion of derivations and linear operators, although it's, as a definition, it's good because it's something intrinsic and doesn't depend on an atlas, doesn't depend on an embedding, etc. Okay, all right, so that's the goal. So the first thing, so let me put this lemma here. So let me this time sort of unusually I have to push things back because I use less space. Okay, anyway, so so that's the first lemma of the day. So to do that, one of the first things we need to say is that you really can just look at an open set around the point and think of the tangent space of P with respect to that open set, and that will be the same as looking at the tangent space of the whole manifold at that point. Okay, so there is a yeah. So somehow again. So let me sort of draw that picture somewhere, perhaps. So here's the sort of the abstractly, this blob is M. Here's a point. Now I'm calling it P, and here's U. Okay, so U, it's an open subset of a manifold, so it is also a manifold in its own right? So sort of any open subset of a manifold, just by sort of is easy to see that it's also a manifold, right? It's a submanifold, in fact, right? It's so you can talk of the tangent space at P with respect to U, and you can also talk of the tangent space with respect to M. And of course, U, there's a map from U to M here, right? So maybe I should have put all this. Let me put this whole picture on the right here. Okay, and then talk of and just draw this sort of the open set, this manifold sort of inclusion map from here to there, and sort of this map P mapping to P here, and so so the first lemma says that this, if you think of this inclusion map of an open set into a manifold, at P, the derivative, this I star, remember I star is the what, I mean, you can also, I also sort of denoted this as di at P. So you can also think of it as the derivative at the point P is going to be a map from the tangent space at U at P on U to the tangent space at P on M, and that's an isomorphism. Okay, so you kind of, it doesn't matter whether you take the whole manifold or an open set around it when you're dealing with tangent spaces at a point. Okay, this is the sort of upshot of the lemma. So what's the proof? This proof. Well, we'll have to use these definitions of what these various tangent spaces are and what these push forwards are. So let me sort of start with sort of setting up what we want to prove. Yes?
Yeah, last time we saw that the locally, if we take C infinity of U and we see the derivation, those, I mean, locally two functions are same, then the action of derivations are also same.
Yes, absolutely. Yeah, that's true. Yeah.
Then actually we may get that TP equal to TPM.
No, they are different. You know, as sets, they are different, right? So one of them is the set of derivations on, you know, these are things that are acting on smooth functions on U, right? And these guys are acting on smooth functions on M. So I mean, a priori, I mean, what you're saying is you're sort of hinting at the proof, which we'll see right now. But a priori, there's no reason. I mean, these are completely different spaces, right? The one is a set of smooth operators on C infinity of M, and another set of smooth operators on C infinity of U, right? And so there is a map between them induced by I. That is this I star, right? The derivative. But then we have to show that that's actually an isomorphism, right? So that's
Yes,
what's
sir.
going on. Okay,
Thank you.
so yeah. But anyway, so yeah, it's nothing very surprising, of course. I mean, you would expect that, yes, I mean, since we know this property, and we'll use that property crucially, we'll use the fact that a function, if some function, you know, sort of two functions agree in a neighborhood of the point P, then you know, when you apply a derivation on it, it's the same value, it gives you the same value. That's an important property that we saw last time. It follows from the Leibniz rule and the linearity. So that's what we're going to use. Okay, so yeah, so you're right. Okay, so anyway, so let's now sort of try to unravel what exactly we have to show. So so suppose, so let x be some you know, tangent vector. When you think of this tangent space to U. And suppose you know, you have that I star of x is 0. Okay, so then you want to show that that this x is actually 0, right? So in TP of U, right? So remember, this is one of the things we also mentioned last time, is that this map is a linear map, right? This induced map. These are vector spaces, and this induced, you know, this derivation is actually a linear map. So if you want to show that this is an isomorphism, you have to show injectivity and surjectivity. So this part will handle the injectivity part. So let me just sort of write that somewhere, maybe. So I'll write it here. So this is sort of, now we are sort of talking about the injectivity part of it. Okay, so so the injectivity is enough to show that, to show this, and what does it mean to be x equal to 0 in TP of U, which means that x of f, maybe I'll change color again. So that is x of f is equal to 0. It's the zero real number. So this is 0 as a tangent vector, right? And what's the 0 tangent vector? Well, whenever you apply it to some function on U, you get 0, right? So for any f in C infinity of U, this is what we want. Okay, so suppose you assume that I star of x is 0, you want to show that this happens, right? Okay, so so what do you do? So yeah, so you have to choose. So remember that you know, sort of yeah. So if you looking at f, it's only defined in this neighborhood, in this open set U, whereas I star of x, if you're 0 as a tangent vector in TP of n, it operates on C infinity of n. So you'll have to use a bump function to, you know, sort of instead of looking at m, looking at U, and that's what we are going to do. Okay, so so you first you know, sort of pick a neighborhood, a slightly smaller neighborhood B of P, such that B closure is contained in U. Okay, so something, maybe let me draw it somewhere here. So maybe I'm sort of, this is the smaller, slightly smaller neighborhood B. Okay, and then you can, so the first sort of claim, so the claim is that you have a there exists a smooth function so here so let's assume that I have a f that I've chosen. All right, so sort of maybe I'll write it, sort of pick any sort of f in C infinity of u. I want to show that I'm assuming this, right? So assuming this, and I want to show that I've picked some f in C infinity of u. I want to show that xf of f is equal to 0. So the first claim is that there exists a smooth function f tilde in C infinity of m now, defined in the whole manifolds, so that this f and f tilde agree on this neighborhood, right? So let's call that neighborhood. Let's take the closure of the neighborhood. So a slightly smaller neighborhood. Okay, so there's a smooth function which so you can, in other words, although f lives on u, you can find some a function defined in the whole manifold that agrees with f at least in some neighborhood of p. Okay, so and how do you do that? Well, sort of the proof of the claim is you
Sir,
can
hello.
yes. Hi.
So one question is basically you want a function that is 1 on B and 0 outside B closure, right?
That's right. Yeah, exactly.
So I mean f tilde B closure or f tilde B equal to f. I mean.
Actually, probably, sir, want the function to vanish outside U, not outside B closure.
Okay.
Anyway, we'll see. Yeah, I mean, it probably doesn't matter whether it's B closure or B here. So we'll talk about this in a little bit. Yeah, so maybe this I probably just need this to agree in some neighborhood. So I might as well take an open neighborhood. So let me remove this. Okay, but how? I mean, so yeah, so this would probably be very easy. But let me just do the claim because we've seen similar arguments before, and the more times you see it, the easier things get. So you choose a partition of unity subordinate to U and M minus B closure. Okay, that's an open cover of M, and you let's call that let's call that partition of unity phi comma psi. Okay, so and so phi is the one whose support lies in U, and support of psi lies in M minus B closure. Okay, so in particular, since support of psi lies in M minus B closure, so this means that psi is 0 on psi. Let me just write this. Psi is identically 1 on B closure, right? Right. So because sorry, I'm sorry, I meant psi is 0 and phi is identically 1. So psi is 0 on B closure, so which means that phi is identically 1 because the sum of these two, phi and psi, is always 1, right? That's what a partition of unity is about, right? So this plus this is the constant function 1. So if one of them is 0, the other one has got to be 1. Okay, so so anyway, so you got that phi is identically 1 on B closure, and so you can just now sort of define so you can just define f tilde of x to be, you can just define it to be phi of x times f of x plus psi of x times f of x. Okay, so so this is sort of the way that you can define. So this f tilde on B, even B closure. So the only thing that will survive is this first term, because that's 0, and then we also know that phi of x is 1, so f tilde equals f on B as we wanted. Okay, so so this is, and it's a globally defined function, right? So it's sort of so the right hand side. So a priori, so f is only defined on U, but the way that we've set it up, actually, so maybe I shouldn't put the psi here at all. So just phi of x times f of x, right? So this is all that we really care about. This, so because f of x is defined only on U, but that's okay because outside it, you know, phi of x is 0 anyway, right? So this you can check is it's actually a smooth function, all right? So this is, and it's globally defined. So this is, let me just write it down. So this is globally defined. So it's now something defined on M, right? And now, remember what we are after. We want to say that x of f is 0, right? So if you scroll back, so to what we want, we are wanting this, right? We have chosen some f and c infinity of m. We are wanting x of f to be 0. But x of f is the same as x of f tilde, right? By the proposition, right? So well, okay, so f of f tilde, I should probably restrict it to U, right, to get a smooth function defined on U. So because this is equal because you know, the f and f tilde agree in a neighborhood of P. Okay, and now this is nothing but, you know, you first do the inclusion map and then define f tilde. So that's what this restriction really means, right? Think of it. And this is by definition, that's the definition of I star of x applied to f tilde. Okay, and this we know is 0 by our assumption. Remember that I star of x we were assuming is 0. So that means that, you know, anytime you feed it any smooth function defined on M, you get 0. So this is sort of by assumption. So let me just write. So this is by our assumption, and this is by definition, right? So I mean the others are by definition, right? So the definition of what push forward of x really means by I. Okay, so this proves what we want, right? So we see that x of f is equal to 0. So this proves injectivity. Now for surjectivity, so surjectivity is sort of a similar thing. It's easier in some sense. Well, so what do you want to show? You want to show that, so remember, what are we trying to show is surjective. So you have this I star map, right? So I star from TP of U to TP of M. And so if you pick, okay, so this time I have to push this forward back. So push this forward so that I have more space. So I star of this I want to show is surjective. So if you, in other words, if I take a y in, so if you take a y in TP of M, then so I want to show that there's some x. So let me place this y over here. So I want to sort of, you want some x here that maps to y, right? So that's what you want. Well, so what you do is you can define a derivation as follows. So this is by setting, so x of f is equal to y of f tilde, where f tilde agrees with f on B, in some neighborhood B. Okay. So that you just extend. So since you have some function, so you're starting off again, let's just like we had before. So you're starting off with some function defined only on U, right? And you extend it to some f tilde that agrees with f on B. And this is something that we just saw that you can do. And now we have some function defined on the whole manifold, and you can apply it to your given tangent vector, the derivation y, right? So on M. So this definition makes sense. Okay, it's well defined, and it doesn't matter what extension you pick, as long as it agrees in a neighborhood of the point, because sort of it only depends on the germ. These derivations, the values only depend on the germ, right? So let me just say that you can check this is well defined. Well, I just said why it's well defined, and it's a derivation. Okay, so it satisfies that Leibniz rule also. So that's sort of an easy thing to check. The fact that it's a Leibniz rule, you just kind of follow your nose and do your calculations. Okay, and this is the this is the tangent vector that maps to y. Okay, so so let me just leave that too as an exercise. So this is and this is let me just say what we want. We want sort of I star of x equals y. Okay, and this again is sort of, you just follow your nose and do the derivations, and you'll get what you want. Okay, so sort of I is just the inclusion map, right? And so so you can use that fact, and you'll see that the definitions would give you that. Maybe if somebody wants, I can do it, but perhaps it's a good exercise. So, yes. Yeah. Somebody's asking.
Starting.
Yeah.
While starting proof,
Yeah.
there was we had taken an open set U and then taken a neighborhood B of X whose closure lies in the open set. To be able to do this, it requires the manifold to be regular, right?
No, this is the manifold is locally Euclidean. So locally Euclidean spaces are always always irregular. And all those nice properties, all those definitions of regular, etc., inspired by Rn, right? So anything you can do in Rn, you weaken the properties that is true for Rn to get all these other definitions in point set topology, or the regular and locally compact, this and that. But here you're fine because you are locally Rn, so all those properties automatically hold. Yeah, you're right. You're right. Okay. All right. So okay. So in any case, yeah. So I just wanted a slightly smaller open set just so that I can write down this open cover, right? So this thing becomes this open cover. Any case, right. So this is the proof that if you TP of M and TP of U are really the same thing. It doesn't matter what open set you're taking when you look at this derivation definition, right? The definition of a tangent space using derivations and these linear operators, etc. Okay, so this allows us to use charts like we were wanting. So if you have a chart around a point P, so U phi is a chart, so it's a phi U to Rn is you can think of this as a diffeomorphism, right? As a smooth map sending U to f of U, phi of U, diffeomorphically, and then you can think of so the tangent space, you can think of the induced map, the level of tangent spaces, phi star TP of U to T of phi of P. All right, and so this is of course an isomorphism. So this is not the corollary. Okay, so the this is the I mean, this is just because this is a diffeomorphism, right? So let me just write it down. This is a diffeomorphism to phi of U. So diffeomorphism to its image, right? And once you have something which is this is something we saw last time. It follows from the functorial nature of these push forwards or these derivatives, that if you are a diffeomorphism from U to phi of U, then the induced map at the level of tangent spaces is an isomorphism. So it follows from this. This we kind of so we saw last time. Okay, but the corollary to this preceding lemma is that since TP of U is nothing but TP of M, right? The tangent space is kind of isomorphic to TP of M. So via this chart now, this phi star, you have an identification of TP of M with T of, okay, let me write it in blue. Sorry, I keep switching around. I'll get used to it. TP of M is isomorphic to this right-hand vector space, which is like one of our usual vector spaces that we think of when we do multivariable calculus, etc. This is the tangent space to a point in Rn, which is something that is familiar to all of us. So via the chart, you can identify TP of U and T phi of PRN, and the preceding lemma tells you that this guy and this guy are also isomorphic. So these are isomorphic, and so therefore, you actually can identify tangent space with a tangent space to a point in Rn. And this is why this is in sort of, you remember that this is the right-hand side is actually, again, it's an n-dimensional vector space. It's actually also Rn, because this is something that you're familiar with. Okay, and you can actually sort of write down a basis of this tangent space, right? So a tangent space, if you're in Rn, you have coordinates and you have coordinate vectors, and you can talk of these coordinate vectors at that point, phi of P. Let me just write it, phi of P. Anyway, so I guess it's understood that it's at phi of P, but you have these coordinate vectors and these n coordinate vectors. These form a basis, right? The span of these, maybe I should sort of do some bracket like this to denote that it's a span, or just say that a basis equals this n. So this is where sort of x1 to xn are the local coordinates around P. In other words, it's that the coordinates around P coming from that chart. So maybe sometimes it's actually sort of these are referred to as not at phi of P, but at P itself, because P itself, sort of you can now think of as a subset of Rn, right? And so you have local charts coming from this particular local coordinates coming from this particular chart that you have chosen. So you can think of these tangent vectors in TP of M as sort of linear combinations of these guys. Okay, so let me just push this next proposition down a little bit. So you can so any tangent vector. So let me just write down any tangent vector x in TP of M is of the form x can be written as a linear combination of these sort of these tangent vectors in these local coordinates. Okay, so you can use these local coordinates to think of tangent vectors that we had described, defined abstractly, like you would in Rn. But this would need this choice of local coordinates, which was what we were trying to avoid in the original definition. But while computation was doing proofs, many times we would need a choice of local coordinates. Okay, and this is one such example where we do need. This is a proposition. Let me sort of push this first.
Sir?
Yes.
Could you update the notes once?
Oh, right. Yeah, sure. Can do that. Yeah. So as I'm, doing it, so you can have a look at these updated notes on the course website. Right. So, yeah, it will be easier for you, so you can scroll up and see what is going. Okay. So anyway, all right. So here's one example of what I'm sort of referring to. So how do these local coordinates, why are they useful? Yeah, any questions? Somebody?
So can you please reshare the screen?
Sorry?
Reshare the screen.
Oh, you folks can't see the screen?
No, sir, I was removed from the meeting, and after
I
rejoining,
was also
can't see the
removed, sir.
screen.
Okay, let me try to. So can you see it now?
No, I can't see the screen.
I also
No,
can't see
sir.
now.
Okay, I don't know what's. Okay, let me start it again.
I can see it now.
Okay, good, thanks. Yeah, all right. Okay, so here's a proposition where you'll see, these local coordinates in action. So in the proof of this proposition, you'll see it in action. So the proposition is something fairly simple and something you would all agree on. And so suppose you have M and N, two smooth manifolds. Maybe one of them is dimension n. Maybe I'll say this is dimension m, this is dimension n. All right, and suppose M is connected. Okay, this is as I said, sometimes we might even assume that all manifolds are connected, but here let me be explicit and say that M is connected. And I suppose you have a smooth map so that the derivative at any point is zero, is the zero derivation, right? So this is so this, I can also think of this as f star, right? So f star is the other notation for this. For any point P, you have some, well, this is from the tangent space at the point P of M to the tangent space of f of P at N, right? So this is the zero linear, is sort of the zero as the linear map, right? So this is what the assumption is, and the conclusion of the proposition is, so then F is, somebody, can you suggest what the conclusion of this would be?
When constant.
Yeah, that's right. Yes, exactly. So then F is constant map. Takes the same value. It goes to the same point in N. Okay, or for all points in M. All right. So this is something that you would expect if the derivative is zero. And so here's the proof, right? So what you do? Well, so suppose you pick a point lying in the image of M. You want to show that actually, so every point goes there, right? So the first thing that you know about this, is that if you look at the pre-image of the point C, then this is a closed set, right? Because, well, it's a pre-image of a closed set. So C itself is a closed set. Remember that, our manifolds are all Hausdorff manifolds anyway, right? So suppose so it's sort of, maybe I should say, well, not want, but enough to show that it is this pre-image of this point C is actually also open. All right, so if we can show that, then it's both open and closed. And since if you assume that M is connected, we know that it has to be the whole of M. So the whole of M maps to C. That would be the conclusion. So the conclusion would be that it's the constant map. Okay, so how do you show that F inverse of C is open? Well, here is where you'll have to choose local coordinates, etc. So let P, suppose I take a point P in F inverse of C in this pre-image set. I want to fit a sort of an open set around P, still contained inside this pre-image set. So choose local coordinates. I'll call it U x1 to xn around P. So here, kind of, when I write down x1 to xn and U, it just means that yeah, I mean, there is some chart in the picture which I'm not calling it phi or anything, but there is some phi in the picture via which you can identify U as some subset of Rn, Rm rather. Sorry, right? So M was M dimensional. All right, so those are the local coordinates around P, and you can also choose a local coordinate around C, right? So V y1 to yn sort of around f of P, which is actually C, right? C. Okay, and you can choose these local coordinates such that f of U contained in V. So you can choose these local coordinates small enough on the target. Let me actually push this down now. Okay, so here's the picture. So somehow, so you have this manifold M. You're looking at this map F, and you have this manifold N. This is the point C. This is point P that maps to C, and you can choose a local coordinate U and a small, chart around. So you can choose charts under U and V, and you can choose these. I mean, charts will come with their own maps. Let's call them phi and psi to Rm, some open sets in Rm and Rn respectively. And here the local coordinates x1 to xm. Here the local coordinates of y1 to yn. Right. So this is what is going on, and what you know. So on U. So what you know is that this derivative of f is zero. Is the zero linear map at P, right? So because that's what we are assuming. So it's every point P in M, this derivative is trivial, all right? Is the zero map, okay? And so this would mean that on U, sort of this map D star of F. Sorry, not D star. So dP, right? So this derivative at the point P. I guess I'm using various notations, so I mean, I hope this doesn't cause confusion. But anyway, what the derivative at some point P is equal to is zero. Well, derivative at every point P. Let me just say that. This x, so for any x in U, dxf is equal to d. Well, this is sort of same notation. Is the trivial is the zero map, right? So this is identically zero, means that at the level of these tangent spaces, means that sort of is a map from so as a map at the level of sort of Rn, tangent space to Rm, so let's call it phi of x to psi of f of x. Okay, it's getting too complicated, but anyway, so it means that at the so this, remember that at the level of charts there is a map here, right? So which is just by well, so these you'll do phi inverse first and then do f and then do psi, right? That gives you a map here. And so you can talk of the derivative of that map. Now that map is from Rm to Rn. Okay, so there your usual multivariable calculus, holds. And so if you talk of that, so this means that so this is the zero map, for all x in sort of u. So if you look at this map at the level of charts and look at the derivative on any one of these points in this open set, then you would, the derivative in the usual sense, in the sense of multivariable calculus, is 0, right? So of this map. Okay, so this is sort of the induced map at the level of charts, and now this is kind of this implies that now you can use multivariable calculus to say that at the level of charts, these maps are constants, right? So you can just say, let me just maybe write some things. So you can say that so df so df of del by del xi. So remember that there's the basis of this tangent space is all these del by del xi's. Okay, and so you can apply this to the tangent vector, and what you get is going to be 0 as a, so now so this is the 0. So this is the 0 derivation, derivation in the target space. So this means that df of del by del xi applied to the coordinate function y, let's call it yj, is equal to 0. And this, by definition, by the definition, the left-hand side is nothing but del by del xi applied to yj composed with f. Okay, so this is this partial derivative. This is equal to 0. So you have that, these functions, all these partial derivatives are 0, right? And so so this, for example, this is equal to 0 for all. So let you fix for some j, you fix a j first, and then if you vary it over all I, then this implies that yj composed with f is a constant function, is constant. Okay, and on u, and this is true not just, I would fix j here, but this is true for all j. This choice of j was arbitrary, and so this just means that f is constant on u. Okay, so this is how you can use this these local coordinates now to talk of these derivations and so on. Okay, so now once it's constant u, you've proved that it is this is open, because this u is some neighborhood of P, and u will be contained in f inverse of C, and therefore f of C inverse is open, and then you're done. Right, so that's how this proof ends. Okay, so any questions about this? Maybe I went over it a bit too fast, but any questions about this? Right, so so this is one example where you use local coordinates and then work with the local coordinates, right? And then you can, I mean, basically the upshot is that whenever you have a manifold, you have a point P, you choose some local coordinates around it. Usually I kind of avoid, I drop drawing this map phi always. So I kind of, I sort of avoid that. And I just say that you have coordinates. This u will have coordinates x1 to xn, and then at the point P, I can talk of the tangent vectors del by del x1, del by del x2, etc. Okay, so what's really going on is that there is a chart, and via the chart you're doing it. But from what we've seen before is that there's an isomorphism. All these things are isomorphic, and so you can talk of these tangent spaces to these points in the chart on Rn. The tangent spaces to points of U, a tangent space to points in M. They're all isomorphic. Okay, so you can think of manifold tangent vectors somehow in the usual sense that you're used to. All right, so even though the formal definition involves derivations and so on. Okay, all right. So so if all this is now clear, let me move on to some to submersions and immersions. So these are some definitions that I'll say now, and sort of this would generalize something that we've already seen before in the context of maps from between Euclidean spaces. So sort of things from multivariable calculus. Okay, so but this is a good time to ask questions if you have any. Let me update my notes. Okay, so so what are submersions? This will ring a bell. So let me define submersions first. So so suppose you have sort of M and N smooth manifolds, and suppose the dimension of M is bigger than the dimension of N. Okay, so this is something that let's assume this. We need it for the definition of submersion. Let me not put brackets here, so it's sort of the dimension dim of M is the dimension of M, right? So and suppose you have a F, a smooth map from M to M, and this is called so this is a submersion at X and M. But usually one talks of, so all these definitions, if you drop this, if you don't say at X, it means that at every point in M. But anyway, so it's a submersion at X and M if d, the derivative of f at X, this goes from the tangent space at N to the tangent space of f of X of N. So this is surjective. Okay, it's a surjective linear map. All right, okay, so this is something that we've kind of seen before, because remember I had talked about, sort of maybe a couple of classes back. So sort of we've seen we were talking of smooth maps from Rn to Rp, where n is bigger than p, and I said something like sort of so the derivative. So we're talking of this, and we're talking of something has rank p, okay, which means that it's surjective. So we were talking of such things, and so this is sort of this definition should remind you of that example. And we've seen the analog. Now we're talking of maps between manifolds, no longer of between Euclidean spaces. All right, So anyway, so but one sort of canonical example of all this is a map between Euclidean spaces. This is called a canonical submersion. Canonical submersion from, let's call it RK to RL. Maybe I should have used M and N, but anyway, it doesn't matter. RK to RL, for K bigger than or equal to L, you have a map that just projects down to the first L. So this is A1 to AK. This projects down to the first L coordinates. All right, and that's a submersion at every point of RK. Okay, so submersion at every point just means that it's a submersion. Yes.
In the definition, also the inequality should not be strict, right? A dimension of M greater than or equal to dimension of N, or should it be strict like this?
Yeah, that's right. Okay, fine. Let me make it. Yeah, good point. Thanks. Yeah, it's best to kind of treat it as a. Yeah. It could be equal. You're allowed to be equal. The identity map between two manifolds can be thought of as a surjection also, as a submersion. All right. Okay, thanks. Okay, so here also I've allowed the K and L to be equal. All right. Okay. So that's a canonical submersion. Okay, so it's easy to see that this, the tangent, the sort of the derivations at every point will be surjective if you just project down from a bigger Euclidean space to a smaller dimension Euclidean space. Okay, so the first sort of the theorem is that actually, so any smooth map which is a submersion at a point would look like a canonical submersion in local coordinates around that point. Okay, so let me just say that, write that down. So if F from M to N is a submersion at X, and Y is the image, then there exist local coordinates around X and Y, around X and Y, such that, well, the local coordinates around X is X1 to XM, let's say. Maybe I should use that M is K dimensional and N is L dimensional. That I think also is less confusing between capital M and small m capital M, small m. So here sort of, maybe I'll write it in different. M is K dimensional, N is L dimensional. Right. So these are smooth manifolds. All right. So in local coordinates, sort of you can write down the map at the level of charts as going from X1 to X K to X1 to XL. These are the local coordinates around X and Y. These are local coordinates RK and RL actually, but I've kind of suppressed the fact that there's a chart in the statement. Yeah, so the point is that in the local coordinates, F just looks like the canonical immersion, right? So sort of the canonical immersion sort of takes only XL is somewhere here, right? So it takes only sort of just this these coordinates. This is the canonical immersion, right? So F looks like the canonical immersion, right? So that's what this theorem says. And sort of if you want to think of it as charts, so sort of the diagram is it's in diagram. So suppose X, Y. Sorry, these are M and N. M and N. You have these manifolds. You have these charts. Phi. So this is a chart to Maybe I should have called this phi of u, but anyways, this is sort of a, let me sort of change my notation a little bit. But so these are charts around that point. Okay, the point x. So this maybe this is bad, but earlier, so these are actually the parameterizations. Okay, so maybe I should have called these phi inverse and psi inverse, but anyway, I'll just sort of ignore my sort of changes with my previous things and just call it this. And so at the level of these charts, there's a map G, and this is the canonical submersion. Because now this U is some subset of RK, and this is some subset of RL, and you can talk of a canonical submersion there. So this is what it means for F at the level of charts being canonical submersion. So anyway, so this we kind of already actually saw the proof of when we were talking of these maps from Rn to Rp. But let me do it nonetheless, do it again. So basically we can apply the inverse function theorem. So so the first thing to do is sort of do the setup and use let's assume that it's actually phi of 0, which is x, and psi of 0, which is y. Okay, so this is, by the way, psi is going to some neighborhood of y on n, right? And so basically I'm sort of centering the chart so that x goes to 0 via the chart. The phi and psi are actually the inverses of the charts, but anyway, as I said, I'm going to ignore the fact that kind of changing my notation here. All right, so so what do you know by our assumption? From our assumption, we know that that this map is the derivative is surjective. So we know. So let me just say by assumption, so we know that the derivative at the point 0 of G, this map, now this is a map between open sets and R in Euclidean spaces, basically. So this from Rk to Rl. So now I'm thinking of Rk and Rl as vector spaces. These are the tangent spaces to the point 0. Right, so this is sort of the tangent space at 0. This is the tangent space at 0. Anyway, this is surjective. This is what we know. All right, and so so what you can do is well, you can assume that that it's the first L variables. It's an invertible map. It's full rank. So this is very similar to what we had discussed earlier. So by a linear change of coordinates in Rn, so it's like a permutation actually. We can assume that in this matrix, this is a k by this right now is a k by L matrix, but you can look at the first L terms, these first L coordinates. So let me just say these partial derivatives. I'll drop the 0. Everything is happening. All these partial derivatives are being evaluated at 0. So you look at these partial derivatives, the first L terms. So this is invertible. So we can assume this. Okay, and in fact, anyway, you can actually post-compose it with a linear map to say it's the identity, but maybe let's see if we can avoid it. Maybe we don't really need it. Okay, so now we define, so this is very similar to what we did before. You can define it from U to Rk. So this Rk, you can think of it as Rl times R k minus L, right? By sending G of any point A in this open set, this was the open set of the chart where all these local coordinates make sense. You can send it to G of A that lives in RL, and followed by the rest of the things, this identity map on the rest of the coordinates that are filled in to make it the same dimension. Remember, we want to apply the inverse function theorem, right? So sorry, this is L, not K, this is L plus 1, L plus 2, up to K. Okay, L, comma, sorry, what did I? L plus 1, A, L plus 2, up to A, K. Okay, all right, and where A is A1, A2 to AK, right? So you kind of it's the identity map on the K minus L variables. And this map is a local diffeomorphism because of the inverse function theorem, right? So by the inverse function theorem, so the derivative of this map, the dg, the derivative at the point 0 is invertible, right? Because so this is similar to what we had last time. So this part would be this matrix. Let's call this, let's give this some name. Let's call it this matrix A. So it'll be A here, and then it will be identity here, and it'll be 0 here. Okay, so this matrix, the derivative of this guy will be invertible. So by the inverse function theorem, G is the local diffeomorphism. And what this means is that G inverse exists and is a diffeo, and is a diffeomorphism from some neighborhood U prime of 0, everything was happening in the neighborhood of 0, into some neighborhood of 0 in U, right? So this is what it means, okay? So there is basically, the point is that the G inverse exists, all right? Now, if you so another thing to notice before we move on is to also notice that where does the canonical submersion come in? So the little g is the canonical submersion from Rk to Rl, composed after G, right? So sort of G composed with canonical submersion gives you little g. This follows just from this definition here. So remember, so what's the canonical submersion? Rk mapping to this factor, Rl. Okay, but this factor is exactly G, little g. Okay, so you can write, little g as this, and so now what happens? So now if you sort of change your chart a bit, okay, so now coming back to the picture, so here we had x, sorry, manifold, it was m to n, and you had u, and you had v, right? You change your u a bit, okay? You change it by, sort of doing, replacing it by u prime. Remember, the u prime is where this G inverse was defined. So this was G, this is u prime. So you kind of shrunk your chart a little bit, okay? So you sort of, it's now you're no longer using u, but you're using u prime. But that's okay, because this composition is still a diffeomorphism. Okay, so because G inverse is a diffeomorphism to some subset, etc. So I've kind of replaced my original parametrization or inverse of a chart, whatever you want to call it, phi, with this guy, which is phi composed with G inverse, right? So you kind of sort of replace phi, which was defined on U, with phi first composed with G inverse defined on U prime. Okay, and now if you now think about it, what happens to so if you do that, then what replaces G? So originally, sort of, G was this map at the level of charts, right? But now this map is going to be you first. So it's going to be something so that if you do G inverse and then do G, you would get that something. So from this orange boxed expression, you can actually see that this guy then was the canonical immersion. Canonical submersion, sorry, canonical submersion here. Right. So this, because again, because since so the G composed with G inverse is the canonical submersion from Rk to Rl. So purely kind of pictorially, you can see all these things happening. So you've kind of replaced this chart. So originally, maybe this little g wasn't quite the canonical submersion, but you've changed your local coordinates, by this g inverse, and so that over here. So now you have maybe I should draw this diagram again. So you have this new diagram where you have this map phi composed with g inverse u prime and psi v, and now this map at the level of charts, this map is the canonical submersion. This is what we wanted, right? So this is what we are after. So any submersion looks like a canonical submersion at the level of charts if you choose the charts properly, and that's what we showed, right? So this is sort of a basic fact about submersions. And as a consequence, we get this generalization of a fact we saw earlier for maps from Rn to Rp. Okay, so a corollary of this is maybe first I'll define what a regular value is. Okay, so because I don't want to keep saying this map is at the level of derivative is surjective, etc., etc. So here's a couple of definitions first. So if f m to n is smooth, then y is a regular value. Somebody had mentioned the word regular. Now you're seeing the definitions. A regular value of f. So y is some point in n, the target space. Okay, so y in n is a regular value of f if the derivative x is surjective whenever x maps to y. So this is surjective. This is, again, was the sort of the condition we had earlier also. Surjective whenever x is in the pre-image of y. So f of x is equal to y. All right, so this is a regular value. And so a consequence of this this canonical submersion, the locally any submersion is a canonical submersion. Maybe I should sort of write that somewhere. This theorem that we saw, can we just so that locally any submersion is a canonical submersion. Okay, so a corollary of this now is this pre-image theorem. So let me call this pre-image theorem. So it says that if f from m to n is smooth and y in n is a regular value, which I just defined, so then the pre-image of y is a submanifold. of M. Okay, and the dimension of the submanifold, the dimension of, let me just say dimension of F inverse Y, is the dimension of M minus the dimension of N. Okay, so so the derivative being surjective automatically implies that the dimension of N must be bigger. The dimension of M, the domain manifold must be bigger, right? Because we saw earlier today that so whenever you have can you guys see this the screen? Is it moving? Do I need to share it again? Let me try to show. I don't know how long you're not able to see my. Can you all see my screen now?
Yeah. Yes, sir.
Okay. All right. So I hope you followed what a regular value is, and this corollary, this pre-image theorem, is something that generalizes what we had seen earlier. Okay, and so why is this a corollary? Well, kind of locally, if you once you have M, N, if you have a regular value Y and a point X mapping to Y, you know that locally this is a canonical submersion, right? So here, if you have coordinates, you know, x1 to xl, okay, suppose this is dimension L, this is K, right? And here this is coordinates x1 to xk, right? So then the theorem that we just proved implies that your map F locally looks like f of x is x1 to xl, right? It's locally a canonical submersion. So which means that what's the pre-image set of y? What does it look like? Here, sort of, I'm kind of assuming that y is the origin, right? So the y is sort of the pre-image. So the y here is really the origin of this coordinates. So this would just look like, well, it would just look like 0, 0, 0, and then you have x l plus 1 to xk. Okay, so so you see that, sort of the local coordinates on the pre-image set is given by these k minus l variables. So k minus l variables, they give you local coordinates here, and it looks like a, sort of this in these coordinates. Once you choose these correct coordinates, this pre-image set would look like a kind of a slice. Okay, so sort of straight, kind of a sort of this is some. This was well. This is something that we've kind of seen earlier. Also, this is sort of something like 0 cross r k minus l. Right. So the first 0. This is a 0 vector in RL, and then you have something where you have your coordinates might be varying. So you're parameterizing this piece of your pre-image lying in this local chart by these many variables, and so this is so locally it is a manifold, and it's in fact by a definition of a submanifold. This is a submanifold, right? So the definition of submanifold was that whenever you can straighten out the your subset into to look like a slice in Rn, then you are always a submanifold. Okay, so anyhow, so this is a corollary now. So now we've seen this generalization of what we were after a few classes back, but we kind of needed these notions first, right? We needed the notion of a derivative, we need the notion of tangent space, etc., etc. Okay, and this in turn gives us lots of other examples of manifolds as submanifolds of a bigger manifold, because whenever you have a smooth map and you have a regular value, then you can take its pre-image and that will give you some submanifold. Okay, so maybe I'll just end with one other example, which is an example of another Lie group, actually. So that you can show as a Lie group, to show that it's a manifold using this pre-image theorem. So so here's the example. So if you take so the orthogonal group of matrices and okay, so this is well, it's a subset of n by n matrices. So let me just say what this orthogonal group is. It's a set of all n by n real matrices, so that AA transpose is the identity matrix, right? And so the claim is that this is a manifold. Okay, so of course, once you know that it's a manifold, it's easy to see that all these group operational and the inverse is actually also smooth maps, and so this is it's a Lie group, right? And so this is an example of a Lie group. So another Lie group. Okay, so another Lie group, exclamation mark. All right, so how do you show this using the pre-image theorem? I mean, there are many ways to show this, but now that we've done the pre-image theorem, it's kind of, this is one way. So you can look at the map from the space of all n by n matrices to symmetric matrices. Okay, so let me call this symbols. These are all symmetric matrices in M, n cross n, R. Now, this symmetric matrices are definitely a manifold, because this is nothing but R of n times n plus 1 by 2, because a symmetric matrix, you kind of vary the values lying in this diagonal and the upper triangle entries, and then you just reflect it across the diagonal, right? So that the symmetric matrices are ones whose transpose is the same as itself. Okay, so so let me just say that somewhere. So sort of A equals A transpose, right? So for any symmetric matrix, and so this is easily parameterized. You can think of it as some Euclidean space. Okay, just like n cross n is Rn squared. This is slightly this is smaller because you have these you need the symmetry. Okay, so you define this by sending f of a. So this will define this to be f of a to go to AA transpose. Okay, so this is certainly a smooth map. Everything depends smoothly on entries, and sort of note that F inverse of the identity matrix, which is symmetric, is actually our orthogonal group. All right, so we can use the pre-image theorem to say that ON is a manifold if we know that this identity matrix is a regular value. Okay, so the claim is that this ID is a regular value of F. Okay, and so how do you show that? Well, so let's talk about the derivative of this map. The tangent space to any point of this manifold, n by n manifolds, is also the set of n by n real n by n matrices. Okay, so this n by n matrices is the tangent space. Just like tangent space of Rn is the same, is also can be identified with Rn, right? Is the vector space. So you can think of, if you think of the derivative of f at a point A, you can think of where this the derivative takes a tangent vector. So this tangent vector B, I'm taking to be in the tangent space to n by n matrices, but this is nothing but the space of n by n matrices. So I'm kind of viewing this B as a matrix. And so what is this? Well, this derivative is nothing but just by definitions, is just A plus some, just sort of perturbing the matrix in this direction. This is how you would do, you can treat this as, sort of something happening in Rn, except that you're arranging your vector in terms of a matrix, a square matrix, right? So you can think of this, the difference in the values of what this f goes, and then divide by s. So you just like an Rn to Rn, because this target is also some subset of n cross n matrices. So you can think of it as a map from Rn squared to Rn squared, if you like. Okay, and so this, if you look at what the definition of f is, so remember that this is sort of A transpose. So this is this minus A transpose divided by S. If you sort of things cancel out, and you're left with BA transpose plus AB transpose. So that's the derivative at any point. Okay, and so you want to say that this is surjective. So in other words, if you're given some symmetric matrix, by the way, this tangent space at any point in symmetric matrix is also a symmetric matrix. So this is sort of yeah, anyway, so let me not write down. So the question of surjectivity boils down to saying that given some C, does there exist some matrix n by n matrix such that BA transpose plus AB transpose is equal to C? Okay, and it turns out that the answer is yes, because if you can just define B to be half of C times A. Okay, so and I leave that to you to check that if you plug in this definition, this B over here, then you would get C. So this kind of shows that all sort of tangent vectors in the target is actually realized. So this derivative is indeed surjective, and that's what we were after. So the identity is a regular value. Okay, so anyway, so this is an example of this pre-image theorem in action. You can show that the orthogonal group of matrices is indeed a manifold, and you can also compute the dimension, because I said that what's the dimension is the difference of these two dimensions of the bigger manifold in this. Okay, so anyway, so next time I'll talk about immersions. We haven't yet got to immersions, so I guess that's leftover. So maybe next time. So immersions would involve the derivative map being injective instead of surjective. Okay, so we'll come to that the next time. So anyway, we'll meet on Wednesday, and once again, if no one has any objection, I'll carry on like this for an hour and a half, and so let me know in case you don't want that. All right. All right. So any questions before I call it a day? I guess these longer classes are a bit